Our story begins in a place of unimaginable scale. It starts not with a world, but with a cloud. Billions of years ago, long before any life existed, a vast, swirling cloud of gas and dust floated in space. This was the Solar Nebula. It was mostly hydrogen and helium, the oldest elements in the universe. But it was also sprinkled with heavier elements, forged in the hearts of long-dead stars. This stardust was the very material from which our world would be made. Within this immense cloud, a gentle but persistent force was at work: gravity. It began to pull the scattered particles of dust and gas together, drawing them ever closer toward a common center. As the cloud collapsed under its own gravity, it started to spin faster and faster, much like a skater pulling in their arms. At the very center, the material grew incredibly dense and hot. This concentration of matter became so extreme that it ignited, giving birth to our sun. Around this new star, the remaining dust and gas flattened into a rotating disk, a protoplanetary disk. It was here, in this spinning platter of cosmic debris, that the planets began to take shape. Tiny grains of dust began to stick together. First, they formed small clumps, then larger ones, in a process we call accretion. These clumps grew from pebbles to rocks and then to boulders. Over millions of years, these collections of rock and ice continued to collide and merge. They grew larger and larger, their gravitational pull becoming stronger with each addition. They swept through their orbits, clearing paths in the dusty disk. One of these growing bodies was the young Earth. It was one of many planetesimals, small, early planets, all competing for material. The process was chaotic and violent. Collisions were frequent and incredibly powerful, releasing enormous amounts of energy. This energy, combined with heat from radioactive elements decaying deep within, turned our young planet into a molten ball of liquid rock. Our Earth, in these very early days, was not the blue and green world we know today. It was a hellish landscape, a glowing sphere of magma. There was no solid ground, no water, and no air to breathe. Its surface was a roiling ocean of molten rock, constantly churning and bubbling under a sky filled with gas and dust. Heavier elements like iron and nickel sank toward the center, drawn down by gravity. This formed the planet's dense core. Lighter materials, the silicates, floated toward the surface to form the mantle and the very first, thin crust. It was a brutal and fiery beginning for a world that would one day harbor life. The early period of Earth's history is known as the Hadean Aeon, named after the underworld of Greek myth. It was a fitting name for a time of extreme conditions. For hundreds of millions of years, our planet endured a period of intense violence. The solar system was still a messy place, filled with leftover debris from its formation. This debris, in the form of asteroids and comets of all sizes, rained down upon the inner planets. This relentless assault is known as the Late Heavy Bombardment. The surface of our world was a cosmic shooting gallery, constantly being pummeled by these massive impacts. Each collision was catastrophic. An impact from a large asteroid would release more energy than all the nuclear weapons on Earth combined. These events would have vaporized any early crust that had tried to form, melting the surface rock all over again. The sky would have glowed red from the heat, and the very ground would have shaken with the force of these cosmic blows. Evidence of this violent era can still be seen today. The heavily cratered surface of our moon is a preserved record of this bombardment, a silent witness to the chaos that once engulfed our planetary neighborhood. Earth, being larger, would have been hit even more frequently. But these impacts, as destructive as they were, also delivered something vital. The comets and asteroids that struck our planet were not just barren rocks. Many of them were rich in water, frozen solid during their long journey through space. Each time a water-bearing comet or asteroid crashed into Earth, it delivered its precious cargo. Over millions of years of constant bombardment, a tremendous amount of water was deposited onto our planet's surface. This was the source of our oceans, a gift from the violent heavens that would prove essential for the next chapter in Earth's story. As the bombardment began to subside, the planet finally had a chance to cool. The immense heat from its formation and the constant impacts slowly radiated away into space. As the surface temperature dropped below the boiling point of water, a remarkable thing happened. The water vapor that had been held in the thick, steamy atmosphere began to condense. It started to rain. This was not a gentle shower, but a relentless, planet-wide deluge that may have lasted for thousands of years. Water poured from the skies, filling the vast, low-lying basins and craters, forming the very first oceans on Earth. With the oceans now formed, the stage was set for life's great debut. But how could life begin from non-living matter? This is one of the most profound questions in all of science. Scientists believe the answer lies in chemistry. The early Earth was a chemical factory. Its atmosphere was very different from today's, likely containing gases like methane, ammonia, and water vapor. Its oceans were a warm, soupy mix of minerals and simple chemical compounds. Energy was abundant, supplied by lightning strikes, intense ultraviolet radiation from the young sun, and heat from volcanic vents on the ocean floor. In these energetic, chemical-rich environments, simple inorganic molecules could have reacted to form more complex organic ones. We call these the building blocks of life. Molecules such as amino acids, which are the components of proteins, and nucleotides, the components of DNA and RNA, could have been created. Famous experiments, like the Miller-Urey experiment, have shown that this is possible. By simulating the conditions of early Earth in a laboratory, scientists have successfully created amino acids from simple chemical mixtures. This suggests that the raw materials for life could have been readily available on our young planet. But how did these simple building blocks assemble into something that could be called alive? One leading idea is the RNA world hypothesis. RNA, a molecule similar to DNA, is remarkable. It can store genetic information, just like DNA. But it can also act as an enzyme, a molecule that helps chemical reactions happen. This dual ability makes it a prime candidate for the first self-replicating molecule. Perhaps, in the primordial soup, short strands of RNA formed by chance. Some of these strands might have been able to make copies of themselves, using the other chemical building blocks floating in the water around them as raw material. Another idea is the metabolism-first hypothesis. This concept suggests that life did not start with a replicating gene, but with a self-sustaining cycle of chemical reactions. Imagine a protected environment, like the tiny pores in rocks near a deep-sea hydrothermal vent. These vents release a steady stream of chemical-rich, warm water. Within these rocky compartments, a network of reactions could have started, using energy from the vent to build more complex molecules. This self-contained chemical engine, or metabolism, could have become more stable and complex over time, eventually leading to the development of genetic molecules like RNA, to record and pass on its successful formula. Whichever path was taken, the crucial step was the emergence of self-replication. This is the very definition of life, the ability to make more of oneself. In the RNA world scenario, this happened when an RNA molecule made a copy of itself. The first copies were likely imperfect. Errors or mutations would have been common. But this was not a flaw. It was an opportunity. Most errors would have resulted in RNA strands that were less efficient at copying themselves, and they would have faded away. But occasionally, a mutation would have created a molecule that was slightly better at replicating, perhaps faster or more stable. This was the beginning of natural selection, acting not on organisms, but on molecules. The most successful replicators would have made more copies of themselves, gradually dominating the chemical soup. Over countless generations of molecular trial and error, these RNA molecules could have become more complex. They might have evolved the ability to build simple proteins, which are far more versatile enzymes. This partnership between RNA and proteins would have been a major leap forward, creating a more stable and capable system. The RNA provided the instructions, and the proteins carried out the work. For these delicate chemical processes to thrive, they needed protection from the outside world. They needed a container. The first cells may have formed when these replicating systems became enclosed within a simple membrane. The building blocks of these membranes, fatty molecules called lipids, form spheres spontaneously when they are in water. If a self-replicating RNA molecule became trapped inside one of these lipid bubbles, it would have a significant advantage. This protocell would have its own internal environment, keeping its precious chemical machinery safe and concentrated, allowing its reactions to proceed much more efficiently. From here, the journey of life truly began. The protocells that were best at surviving, replicating, and passing on their traits would flourish. Eventually, a more stable molecule, DNA, would take over the role of storing genetic information, leaving RNA to focus on its role as a messenger and worker. This transition gave rise to the first true living cells, the ancestors of all life on Earth. The epic journey was complete. From stardust swirling in a nebula, to a molten ball of rock, to a water-covered world, our planet had finally become a home. The simple chemistry of the early oceans had given rise to the miracle of self-replicating life, setting the stage for billions of years of evolution to come.